So we are dealing with the 8th problem in this series, and the 8th problem in this series is problem number 1.85. The problem is stating a small sphere of mass m suspended by a thread is first taken aside so that the thread forms the right angle with the vertical and then released. Find the total acceleration of the sphere and the thread tension as a function of theta, the angle of deflection of the thread from the vertical. The thread tension at the moment when the vertical component of the sphere's velocity is maximum, and the third part, the angle theta between the thread and the vertical at the moment when the total acceleration vector of the sphere is directed horizontally. So we have these three problems that is to be discussed from this problem, which is an example of a non-uniform circular motion. So the first thing that we construct is the circular path which the problem is discussing about, and over here we consider this as the point from where the mass is released. This is the point of pivot, the center is the point of pivot, and this is the sphere which we are discussing about, having a mass m. So it is released from this point when the angle is 90 degree, and now when the sphere is at this point, which we consider at an angle theta with the vertical, the problem is asking us to evaluate the following aspects. So the first thing that we need to understand that as this sphere descends over here, it is following a circular path, and at this instant of time it will have a certain velocity v. We consider the lowest point in its path as the point of reference level, and therefore over here if we calculate the height at different places, so at point A from where the sphere is released, it is at the length of the thread which is equal to L, and if this is L, so this is going to be L cos theta, and this height is going to be L minus L cos theta, L minus L cos theta. So this is the essential thing that we need to understand, that the distance which the sphere covers while moving from point A to P, P is the point which we are discussing over here, so this is L cos theta, and as it reaches here it will have a certain velocity which we are referring over here as v. We also draw one more circle to explain the other aspects of the motion, where we will be discussing about the acceleration aspect. So this is just the replica of the same system. So at this point P, it will have two component of acceleration. One will be a radial component of acceleration which we mark as AR. The another will be tangential component of acceleration which we mark as AT, and due to both of them there will be a net acceleration which is vector sum of these two acceleration, and we consider that this net acceleration is making an angle theta with the tangential acceleration. Now at any given angle theta, we can say that the tangential component of acceleration can be simply evaluated by just constructing the FBD of the particle. So at any point of P, we can consider that this mass m is exerting its weight in the downward direction, and if it is making an angle theta with the vertical, then over here we will have one component as mg cos theta and the another component as mg sin theta. So this mg sin theta is responsible for the tangential component of acceleration. So the tangential component of acceleration at can be simply written as g sin theta. So at any angle theta, the tangential component of acceleration will be g sin theta. Now to evaluate the radial component of acceleration, we need speed v at this instant, as radial component of acceleration is v square upon r. In this case, r being equal to L. So to calculate v, we are applying energy conservation between A and P. So total energy at A must be equal to total energy at P. So energy at A with respect to our reference level is equal to mgl. Energy at P is equal to mgl minus L cos theta, and followed by this we will also have kinetic energy half mv square. At A, speed is 0, so there is no contribution of kinetic energy, and at point P there is presence of kinetic energy, which is half mv square. And if we solve this, mgl cancel out, so mgl cos theta equal to half mv square, and then we can write that v equals 2gl cos theta square root, or we can simply write v square also. So this is by applying energy conservation between A and P, and hence over here if we need the radial component of acceleration, which is v square upon r, so we write it as 2gl cos theta upon L, and we get this value as 2g cos theta. So we have a radial component of acceleration and we have a tangential component of acceleration, and therefore the net acceleration is going to be vector sum of at and ar, which we have discussed here. And at and ar are perpendicular to each other. So since they are perpendicular to each other, so vector sum for two perpendicular vectors can be calculated as at square plus ar square, and over here on solving we get the magnitude of acceleration as g 1 plus 3 cos square theta square root. So this is the first part of the problem which we have, the total acceleration of the sphere, which we calculate over here. And if we calculate the tensional force, which is also asked in this problem, so tensional force T at this instant will be contributed by mg cos theta, and because of the speed v, we will also have mv square by L. So therefore tensional force can be written as mg cos theta plus mv square by L, v square being 2gl cos theta. So therefore tensional force is going to be 3 mg cos theta. So both these answers combined form the first part of the problem. Now the next part of the problem is asking us the thread tension at the moment when the vertical component of the sphere's velocity is maximum. So as we can see that the speed v is along the tangent to the circular path, so we need to calculate the vertical component of speed v. So let us again construct the trajectory which we are discussing. So if this is the circular path that we have, then at this point, which we are referring as a point P or any random point, we have a velocity v or speed v, and we can have two components of this speed v. So if this angle is theta with the vertical, so this angle is also theta and over here we can say that this is 90 degree, this is 90 minus theta, again a theta component, so v cos theta, and this one is going to be v sin theta. So we have a v cos theta component which is directed in this direction, v cos theta, and we have a v sin theta component which is in this direction. The speed v is already calculated in above, so therefore the vertical component of speed, the vertical component of speed, which is v sin theta, so therefore we write it as, so we have 2gl cos theta square root, and then we have this sin theta term. Now the problem is asking us the thread tension at the moment when the vertical component is maximum. So we have this v vertical which we are writing it as vv, and we want to maximize this. So therefore to maximize this we write dvv with respect to d theta being equated to 0. So over here we can write root 2gl being constant. We have root over cos theta and sin theta which is to be differentiated. So root 2gl being constant. So if we keep root cos theta constant and differentiate sin theta, we get cos theta. And then if we keep sin theta constant and differentiate root sin theta, root cos theta, we get half of by cos theta, and then cos derivative is sin theta, and we equate this to 0. And over here on solving, you can see that we have equating this part to 0, and on solving we obtain this value cos theta equals 1 by root 3. So derivative of cos theta can be written as minus sign, so there should be a minus sign, so which we are making this one as a minus sign. So we have an expression like this, and we equate it to 0, and on solving we obtain tan square theta equals 2, and therefore cos theta, which is needed for the problem, is equal to 1 by root 3. So now what we do is we put this value of cos theta. So in the tensional equation we have 3 mg cos theta. So 3 mg cos theta by root 3, that is cos theta is written as 1 by root 3. So we get root 3 mg. So for B part, the required answer for tension is 3 mg cos theta, which is equal to 3 mg by root 3, that is root 3 mg. So we have solved so far the first part and the second part of the problem. This was the first part of the problem which we are writing as part A, and after this part A we are solving the second part of the problem which is part B. Now there is a third part of the problem. The angle theta between the thread and the vertical at the moment when the total acceleration vector of the sphere is directed horizontally. So if we think in terms of total acceleration of this sphere, so over here we have marked the radial acceleration and tangential acceleration, and we have taken this angle as theta. So over here we are saying this is the net acceleration. So the problem is asking us for the net acceleration to be horizontal. So if this net acceleration is horizontal, then we can say that this tan theta, if in this triangle, if we construct this triangle like this, so over here we can say that tan theta equals AR by AT. So tan theta equals AR by AT. So we are solving the third part of the problem. Tan theta, which is equal to AR by AT. AR being 2g cos theta and AT being g sin theta. So So we can write this as that tan square theta equals root 2. So theta equals tan inverse of root 2, and over here we get the value 54.7 degree. So this is the third part of the problem, the angle theta between the thread and the vertical at the moment when the total acceleration vector of the sphere is directed horizontally. So this is how we solve this particular problem. This is a very wonderful problem, problem number 1.85, where we consider every small aspect of the circular motion of the particle which is released from a certain point, and as it covers its motion, we have discussed several aspects about its motion.